This conference will now be recorded.
All right, Math 211 students, this is section 3.5 and we're still looking at curve sketching. I'll be doing this video in a couple parts probably because of the length of each problem. So remember, this is an 8-step process and I'm going to walk you through it for a few different varieties of functions or equations. So the first step is always to figure out the domain that you're dealing with. And for this one, this is a polynomial. So the domain would be all real numbers or negative infinity to infinity. And this is just factored form of a polynomial. So that is still a polynomial. Number 2 is to find the y-intercepts and x-intercept. So y-intercept should be singular and x-intercept could be plural. Don't know yet. To find the y-intercept, you plug in 0 for all the x's. Well, that would make this 0 times negative 64, which is just going to be 0. So that's going to be 0, 0. And if you set each part equal to 0, because we set y equal to 0 when we solve for the x-intercept, you get that either x had to be 0 or x had to be 4 to make that happen. So this would have been 0, 0, and 4, 0. The third step in the 8-step process is to figure out if there is going to be any symmetry. So remember, we're testing for even or odd functions essentially. So f of negative x is what you want to plug in. So this would make this negative x and then negative x minus 4 cubed. Now this one takes a little bit of work. This would be a negative x. This, you want to pull a negative 1 out of the factors here, so that makes this now x plus 4 cubed all together. And then we can cube just the negative 1 now that it's been factored out. So that would be negative x times a negative 1 cubed, which would be negative 1. And then we'd still have our x plus 4 then cubed. So this actually ends up being x times x plus 4 to the third. Now to be even, after plugging in negative x, you have to get the original function exactly, and we did not because we now have an x plus 4 inside here. To be odd, you have to be able to pull a negative out and it be the same function. If we pull a negative out, it's going to change this to a negative. So it's not going to be either even or odd. So neither even nor odd. So we don't have the symmetries that go with those. Step 4, we're going to now look for asymptotes. Now, if it's a polynomial, you shouldn't have asymptotes. Then we move on to step 5 in the process, which is to figure out the first derivative and then to find those critical numbers. And we're going to tell whether or not we're increasing or decreasing on specific regions. So to take the first derivative, you have to realize that this is, let me write my function over here. This was the y. It was x times x minus 4 to the third. I mean, if you FOIL all that out, that's going to be pretty messy. So we're going to go with just taking the derivative as a product rule. So this would be first times the derivative of the second, which would be 3x minus 4 to the second times the derivative of the inside, which is a 1, plus second times the derivative of the first, which is derivative of x, just 1. We're going to clean that up. So that's going to be 3x x minus 4 squared plus x minus 4 to the third. We can factor out an x minus 4 squared. That leaves us with a 3x plus an x minus 4 to the first. So we get x minus 4 squared, and this is 4x minus 4. Now if we want, we could pull, since this is not got any exponent on it, we could pull that 4 to the front in that common factor pair, and that would just be an x minus 1 then. Okay, so then when you look at this, then it's easy to see that our critical numbers are the places where those factors would equal 0. And since this is a polynomial, we're not going to have any place where the derivative does not exist. So the critical numbers happen at x equals 4 and x equals 1. So then we would place those on our number line for our test values. So 1 is first because it's least, then 4. This is the region negative infinity to 1. This is the region 1 to 4. This is the region 4 to infinity. We pick a test value in each region, so 0, 3, and 5. You plug it into y prime, and you're just checking the signs. So we have a positive always for the 4 that's in the very front. then we're going to be timesing this by, if we plug in 0, that's going to be negative 4 squared, which is going to come out positive. Plug in 0 here, though, you get a negative. So positive, positive times negative is going to be an overall negative. So this region is decreasing. And then in the next region, we have the positive for the 4. 3 minus 4 is negative 1, but you square it, so it comes out positive. And 3 minus 1 is positive 2. So 3 positives multiplied together is a positive, so that region is increasing. And then we get all positives again for the last one. So that means that this region is also increasing. So remember, to get a local max or min, you have to change from decreasing to increasing at a place that the function exists. So we know even though that's going to be step 6, we're going to talk about that in a second, but we want to at least describe the regions that we're decreasing and increasing on. So we're decreasing on negative infinity to 1, and we're increasing from 1 to 4 and 4 to infinity. Okay, and then for 6, we're looking for the only place that we had a change of sign, which was decreasing to increasing, which is a minimum. So we have a local min value, we don't know the y value yet, at the x, which was at 1. So if we want to find that value, we have to plug 1 back into the original function. So that would be 1 times 1 minus 4 cubed. That's 1 times negative 3 cubed. That is 1 times negative 27. So this is going to be negative 27. So that is that place where we have a local minimum. If you want to write that as an ordered pair, it'd be 1 negative 27. Now for part 7, we want to take the second derivative and we want to find out if we're concave up or concave down. And I'm actually going to write this back over here. So for 7, so remember, this was our final form of y prime, so we're going to use that when we take our next derivative. You can kind of think of the 4 just being out front of the whole thing if you want. And this is going to be product rule again. So it's going to be first times derivative of the second, which would just be a 1, plus second times derivative of the first, which is going to have a chain rule and a general power rule going on. So 2 times x minus 4 to the first times the derivative of the inside, which is a 1. So this y double prime is 4 bracket x minus 4 squared plus 2 x minus 4 x minus 1. Notice I'm not going to distribute those out because they share an x minus 4 in common. So we can pull that x minus 4 outside of the bracket. That would leave me with an x minus 4 plus a 2 times an x minus 1. So we have 4 parentheses x minus 4. Then in the bracket, this is going to be a 2x minus 2 if you go ahead and distribute that. So I'm running out of room. So this is 3x minus 6. And if you want, again, you could pull that common 3 out. That would make this a 12 in front. So 12, x minus 4, and x minus 2. That just makes it easier to see where it makes each of those equal 0. So it looks like the possible places where our concavity can change, or we could have possible points of inflection happen when x is either 2 or 4. So these are possible inflection points. We don't know for sure yet. So we're going to check that. And that'll also be a place where we can check for concave up or concave down. So we have 2 and 4. So this is negative infinity to 2, 2 to 4, 4 to infinity, 0, 3, 5. Just so happens I picked the same numbers because they were in my intervals. And we're going to plug, remember, these into our y double prime. So 12 is always positive. And then we have plugging in 0 gives me a negative and another negative. Multiply those together, we get a positive. So that means we're concave up in this region. If we plug in 3 here, we'll get a negative in the first one, but a positive in the second one. So that comes out negative, which means we are concave down. And then for the last region, we get positive, 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 which means we are concave up again. Now, as long as these are defined values for the function and they change from concave up to concave down on either side of them, then that means that we have a point of inflection. So first of all, I'm going to write we're concave up on negative infinity to 2 and, 4 to infinity. and we're concave down on 2 to 4. Now my points of inflection or inflection points are going to happen at 2 and 4, but we need the y values for each of those. So if we plug them into our original function, 2 times 2 minus 4 cubed, and 4 times 4 minus 4 cubed, this guy gives us 2 times negative 8, so that's negative 16. So 2, negative 16 is one of our inflection points. And the other one happens at, this is 4 times 0, so that's going to be 0. So this would be 4, 0, which was one of our x-intercepts. Okay, so let's graph what we know, because that's part 8. So step 8 is to graph everything we know. So we know we have a y-intercept at 0, 0. We have another y-intercept at 4, 0. We know that we have a local minimum at 1, negative 27. So we need to kind of determine how we're going to count on this, because I don't have huge graphs. I'm going to count by negative 3, negative 6, negative 9, negative 12, negative 15, negative 18. So I'm counting by threes, 24, negative 27. I'm going to count by ones on this, and I'm going to count by threes on this. So it's going to be sort of scaled in differently, but that's the only way we can make it fit on the graph. So 1, negative 27 was a min. Sometimes it helps if you write that. You can erase it at the end. We don't want it on our final answer, but it helps you see that that's the lowest you can get right here. And we are supposed to be decreasing from negative infinity to that 1. So that means from here all the way down to here, we were decreasing. So from negative infinity to that point. So we have this decreasing function, which hopefully we draw better than I just did, because we want it to cross on our actual point. It's always harder to draw using a artificial pen. So it's coming down and it's finally hitting there. Notice that this also is concaved up all the way until 2. So when we get to 2, negative 16, remember that was our point of inflection, which is about right here. That's when our concavity will flip. So instead of being concave up, we're now going to be concave down from 2 to 4. And then we're going to go concave up, and we're still increasing here. So that means we're not flipping back down. We're actually continuing up. So these are my points of inflection. They're also, one of them is an x-intercept. We are decreasing, increasing, increasing, concave up, concave down, concave up. So there is that one. Okay, I'm going to try to do one more before I end part 1 of this video series. And we're going to look at this other polynomial that was on here. This one has some fractions involved. So I'm going to use a different color. So the first thing is domain. Since it is still a polynomial, the domain is going to be negative infinity to infinity. The intercepts, we're going to try to see what we can find. The best way to try to find your intercepts is going to be to try and solve this by, first of all, pulling out an x, because they all have an x in common. I'll do my y-intercept first. It's easy. If you plug in 0 for all the x's, you get 0. So it's going to be 0, 0. But for x-intercept, possibly plural, we're going to come over here and put 0 equals all of this. So that's 1/5 x to the 5th. You have to at least try to see if you can solve it. So this is pull out an x. So that gives me 1/5 x to the 4th minus 8/3 x squared plus 16. We know x equals 0, so we already know that guy because we had 0, 0 for our y-intercept. So we're just going to worry about this fractional piece. And anytime you have fractions and you have set it equal to 0, you can multiply everything by the LCD to get rid of those fractions. So that would be 15. So that's going to make this 3x to the 4th. That would be minus 40x squared. 15 times 16, I believe, is, 240 equal to 0. I then checked to see if this was even worth using doing the quadratic formula on by just checking b squared minus 4ac. Because remember, if that comes out negative, that means this is imaginary and you don't need to attempt it because you're not going to get any solutions on this number line from that. And this definitely comes out negative overall because that, and I can show you really quick. In fact, we'll find the number. This is 40 negative squared is going to be positive, so that's going to be 1600 minus, and that is 12 times 240. Yeah, so notice this is like negative 1280, which is imaginary because this is the part underneath the square root. So that means this is the only x-intercept we're going to get from the graph because it's the only real number. Now for part 3, I went through to check and see if we had the symmetries. So I put in negative x for all the x's. So this is 1/5 times negative x to the 5th minus 8/3 times negative x to the 3rd plus 16 times negative x. A negative in an odd power comes out and changes the sign to a negative, so that's not negative 1/5 x to the 5th, and that would make this positive 8/3 x to the 3rd and minus 16. Now that is not the original function, but if you pull a negative 1 out, it is the original function. So, and this is an x, by the way. So what that means is that this is what we call an odd function, which means we have origin symmetry. So that's nice to know for graphing purposes. Okay, for step 4, we want to look for asymptotes. Again, this is a polynomial, so there should be no asymptotes. For 5, we're going to take that first derivative. So y prime would be 5 times 1/5 is just 1, so that's going to be x to the 4th. 3 times negative 8/3 is just going to be negative 8, and then we lose the power, so that's x squared. And 16x's derivative is just 16. So notice this comes out nicely. And this factors into x squared minus 4 and another x squared minus 4. And then both of those factor into x plus 2, x minus 2, x plus 2, x minus 2. So we get some multiplicities here. We have 2 different possible critical numbers, -2 and +2. They just show up more than once. We're going to put them on our number line to check for increasing and decreasing. So this is -∞ to -2. Always make sure you put these in order from least to greatest, otherwise your number line doesn't make sense. I'm going to use -3, 0, and 3 for my test values. So if we plug those into y prime, this would be a negative times a negative times a negative times a negative. So 4 negatives is going to make a, wait, hang on, did I say that right? -3, oh no. -3. Yes, I'm right. Okay, just making sure I wrote everything right. So this is positive overall, so that means this region is increasing. If we put in zeros, we get alternating signs, positive, negative, which makes an overall positive, which means it's also increasing. And we have a 3, we also get now, it's going to be positive for all 4, which means it's also positive, which means this function is continually increasing. So when we normally would write this, we would say it's increasing on -∞ to -2, then -2 to 2, and then 2 to infinity. So because this function is continuous and it's a polynomial, that means, so I'm going to write a couple notes. So it's continuous on the reals because it's polynomial. That means we're actually increasing all the time. So increasing on -∞ to infinity, essentially on the reals. Okay, so our part 6 is, are there any local maxes or mins? And that would be a no, because we didn't have any changes between increasing and decreasing. So no local max or local min. Okay, so we're getting on almost to the end. Step 7, we need to take a second derivative. So look back here at your first derivative right there. And that would make this 4x to the 3rd minus 16x we would factor out of 4x. That makes that x squared minus 4. Factor that again. We get x plus 2 and x minus 2. So possible places where we could have concavity changes are -2 and 2 and 0. So we'll put all three of those in least to greatest order. So this is -infinity to -2, -2 to 0, 0 to 2, and 2 to infinity. We'll pick test values in each region. And we're going to plug the member into the second derivative to see if it's concave up or concave down. And you could plug it right into here if you want, or into the factored form. Either way, doesn't matter as long as you check your signs. So this will be I'm going to use the factored form. So this is negative, negative, and negative, which is 3 negatives, which means this is concave down. If we plug in -1, we get a negative, a positive, and a negative, which comes out as a positive, so that's concave up. If we plug in 1, we get a positive, another positive, and a negative, which comes out negative, which means concave down. And then at 3, we get all 3 positives. So that makes for concave up again. So concave up on -2 to 0 and 2 to infinity. Concave down on -infinity to -2 and 0 to 2, which means we do have points of inflection. -2 is one of the x values where that happens, where we change concavity. At 0, we also change concavity because you go from positive to negative, and at 2. So what we need is the values for each of these. Now we already know the 0 because remember 0, 0 was one of our x-intercept, y-intercept points. If we plug -2 back into the original function, and just to save us time, I use my calculator for this, it comes out as -256 over 15, but you'd have to plug it back into that original function with the fractions. And since we have origin symmetry, that means since this is both negative, these are going to be matching, but both positive. So it's 256 over 15, which comes out to roughly 17 and 1/15, just for reference points. Okay, so let's plot what we know. We have 0, 0 is the only x and y intercept. We know that it's an odd function. That'll help us sketch it. So essentially, we need to plot all the other information. So if we count, what did I count by? I think 2's. So I counted this region by 1 and this region by 2's. So we're going to have to go down to -17 over 1 and 1/15. So if we're going to -2 and then down -2, -4, -6, -8, 10, 12, 14, 16, 18. So -17 and 1/15 is going to be somewhere around there. And then we have a similar point up here. So we go +2 and then up 2, 4, 6, 8, 10, 12, 14, 16, and then about 17 and 1/15. Okay. Now, what we do know is that we're increasing the whole way up, but we have some changes in concavity, remember. So we are concave down, I believe, on the very first region, which is from -infinity to -2. So that means from here to here, we are concaving down. But then from -2 to 0, we're concave up. So the bowl flips as we head towards this guy. And you have to forgive me, it's really hard to draw on this. There we go. So concaved up. And then at 0, 0, we change again and we become concave down again. So notice, and this is supposed to be concave up. It's really hard to draw it. I'm going to redraw this region. You want it to look as best as possible, and it's just a little difficult. So this is concaved up, so it shouldn't have curved right there at the end. And then this is concave down. And then at the very end, again, we go concaved up. And notice that we have the symmetry. So that's the best I can do on this graph. So there are 8 steps, and this is the end of part 1 because these videos, like I said, are a little long. So the next video will contain 2 more examples of how to graph using curve sketching.